Hello everyone. Today I'll guide you on how to use the NUV Optimization Solver. We'll demonstrate the tool's usefulness by applying it to tackle some challenging inequalities and systems of equations from IMO contests. Now, you've probably heard of the IMO before, but just to give a quick overview, IMO stands for the International Mathematical Olympiad, a competition for pre-university students. It's held annually, starting from 1959, and has over 100 countries participate. The standard format requires participants to solve 6 problems over 2 days. Almost every year, the problem set includes at least one inequality problem and/or an equation-solving problem. You can explore all the past IMO problems at www.imo-official.org/problems.aspx. For solutions, you can visit Art of Problem Solving's wiki. I'll include all the links we referenced today in the description below. Now let's talk about why inequalities in systems of equations are so central, and how we can leverage the NUV optimization solvers to tackle them efficiently. It's no coincidence that inequalities in systems of equations appear so frequently in the IMO. Throughout history, from thousands of years ago to today, solving equations and optimization problems has been essential, whether you're measuring land or controlling a robot. Today, with AI becoming increasingly influential in society, skills in inequalities, optimization, and equation solving are more important than ever. They form the foundation of deep learning, machine learning, and AI, affecting both education and broader societal applications. Here's a quick summary of how to use the NUV optimization solvers for a specific problem. Step 1. Formulate the problem correctly in mathematical terms, as an optimization or equation-solving problem. Remember, a single question can have multiple formulations, and choosing the most convenient one is often key. Step 2. Enter your formulation into the NUV Optimization App, select an appropriate solver, and run it. For more guidance, check the official user guide on our website with the link in the video's description. Step 3. Review the results produced by the solver. If necessary, run it again with the same algorithm or try a different algorithm for comparison. These steps might seem abstract, so let's see how to apply them to a concrete example. This example comes from problem 3 of the 1973 IMO. At first glance, it looks like a mix of equation solving, specifically finding the roots of a 4th-degree polynomial, and inequality. Step 1. An initial idea might be to use certain criteria on the parameters a and b that guarantee this equation here has at least one real solution for x. Interestingly, such a criterion exists. You can find it on Wikipedia under the section Nature of the Roots on this Wikipedia page. In theory, we could formulate this as a constrained optimization problem in 2 variables, a and b, using that criterion. However, the resulting formulas are quite intimidating. There's also a solution provided on the Art of Problem Solving page that we can reference. As noted there, the first posted solution contains some errors, and while another solution exists, it's rather long and complicated. So, can we find a simpler way? Yes, and here's one possible approach. We'll formulate this as a constrained optimization problem in 3 variables, x, a, and b, instead of just 2. The problem is written as minimize a square plus b square, subjected to the constraint x to the 4th plus ax cubed plus bx squared plus ax plus 1 equals 0, where a, b, and x are real numbers. Next, let's input this problem into the NUV Optimization app. First, you can visit nuvoptimization.com, then click on Guides, User Guide, and open the PDF file. In particular, refer to Section 2, which explains how to enter problems into the app. Since our problem involves 3 variables, we can label them as x0 for x, x1 for a, x2 for b. With this assignment, our problem becomes minimize x1 squared plus x2 squared, subject to x0 to the power of 4 plus x1 times x0 to the power of 3 plus x2, x0 squared plus x1, times x0 plus 1 equals 0. Now let's open the NUV Optimization app. Since this problem has 3 variables and only 1 constraint, you can use a free account. You have several login options here. You can use the demo account, your own account, or simply sign in with Google. For simplicity, I'll use the demo account in this example. After logging in, you'll arrive at the main solver screen. First, under Task and Algorithm, choose Constrained Minimization. Next, select an algorithm. You'll see 7 available options, ranging from gradient descent at the top to algorithm 4 at the bottom. As explained in the user guide, the algorithms lower on the list are generally more robust but slower, while the ones higher up are faster but maybe less precise. For instance, gradient descent is usually quicker, whereas algorithm 4 tends to give more accurate results. To start, let's choose backtracking gradient descent. We can always come back later to compare results with other algorithms. Since our problem is not stochastic, we can skip the 2 boxes on the second row. Now, moving to the third row. For number of variables, enter 3. For number of objective functions, enter 1. For number of inequality constraints, enter 0. For number of equality constraints, enter 1. And for number of running steps, that's the maximum number of iterations, enter 100. We can leave the remaining boxes as they are. Once that's done, click Submit. This will open new boxes where we can enter our objective function and constraints. For the objective function, type x1 squared plus x2 squared. Then, under Enter the Equality Constraint Functions, find the box labeled Constraint Function 1 and enter x0 to the power of 4 plus x1 times x0 to the power of 3 plus x2 x0 squared plus x1 times x0 plus 1. Remember, as noted in the user guide, you don't need to include equals 0 for equality constraints. Once everything is entered, click Minimize and wait for the result. Now here come the results. First, you can see a summary of the problem setup and the algorithm we selected. The table starts with iteration 0, which represents the randomly generated initial point. Here, the first coordinate corresponds to x0, which equals 0.0967. That's our x value. The second coordinate, x1, is our a value, equal to 0.833, and the third coordinate, x2, is b, equal to 1.684. The value of f of x is the objective function x1 squared plus x2 squared, which at this initial point equals 3.5316. The app displays several of the first and last iterations so that you can observe how the values evolve. At the final iterate, we obtain x0 equals negative 1.008, x1 equals 0.906, x2 equals negative 0.187, and the corresponding function value, f of x, equals 0.856. Now let's compare this with the exact solution from the Art of Problem Solving website. According to the official solution, the minimum value is 4/5 equals 0.8, occurring at a equals plus or minus 4/5 equals 0.8, plus or minus 0.8, and b equals negative 2/5 equals negative 0.4. So, our solver result is already quite close, but we can improve it further. We'll change the number of running steps from 100 to 300. Click Submit, re-enter the objective function and constraint, and then click Minimize again. This time, the result is noticeably better and even closer to the exact solution. Next, let's experiment with a different algorithm. Gradient descent. We switch to that, keep the same problem setup, and run it. It runs very quickly, but it doesn't converge. You can see that both the point and the objective function values start diverging toward infinity. This could be because our learning rate is too high. So, let's go back. Set enter the learning rate to 0.01 and try again. Once more, gradient descent runs very fast, but again, it diverges. So, it seems gradient descent isn't suitable for this particular problem. Finally, let's switch to algorithm 4 and test with 100 iterations. This time, it runs quite efficiently, and the result is very close to the correct solution. Now that we know how to use the NUV Optimization app, let's practice with another IMO problem. Specifically, problem 3 from the 2006 competition. Here's the problem. According to one proposed solution, the optimal value of m is 9 divided by 16 times the square root of 2, which is approximately 0.3977. We can see that this solution provides a proof. However, at the end it even notes, the solution isn't correct and it's missing a ton of steps. So, can NUV optimization help us verify or even improve this result? Let's find out. A key step, as always, is to start with a precise mathematical formulation. Let's perform a few algebraic manipulations first. We start from the inequality. The absolute value of AB times a squared minus b squared plus bc times b squared minus c squared plus ca times c squared minus a squared is less than or equal to m times the square of a squared plus b squared plus c squared. Now, if we divide both sides by that same square, meaning by a squared plus b squared plus c squared squared, we get that the absolute value expression divided by a squared plus b squared plus c squared squared is less than or equal to m. That means our optimization problem can be stated as find the maximum over all real numbers a, b, and c of the absolute value of ab times a squared minus b squared plus bc times b squared minus c squared plus ca times c squared minus a squared minus c squared plus ca times c squared minus a squared divided by a squared plus b squared plus c squared squared. Strictly speaking, we should call this a supremum instead of a maximum. If you've taken calculus, you'll recognize that concept. But to keep things simple, we'll just say maximum. Since the NUV Optimization app only solves minimization problems, we can convert this into a minimization task using a simple trick. The maximum of a function f is the same as the minimum of negative f, so we can restate the problem as minimize the negative of the absolute value expression divided by a squared plus b squared plus c squared squared. Technically, this should be written with infimum instead of minimum, but we'll keep the lightweight phrasing here. This problem involves 3 variables, a, b, and c, and no constraints. That means we can still use a free NUV optimization account. We'll assign x0 for a, x1 for b, and x2 for c. According to the user guide, the objective function to enter into the app should be written as follows. Now let's run the problem using algorithm 4 in the NUV Optimization app. We'll set the following parameters. Unconstrained minimization, algorithm 4, no stochastic option, number of running steps equal to 100, number of variables equal to 3, number of objective functions equal to 1, and both the number of inequality and equality constraints set to 0. After running it, we can see that the result found by algorithm 4, once we take the negative of it, since our function is the negative of the original one, is very close to the optimal value. That optimal value, as given in the problem statement, is m equals 9 divided by 16 times the square root of 2, which is approximately 0.3977. You can also experiment on your own with other algorithms and other problems to explore how the NUV Optimization app behaves in different scenarios. Thank you for watching, and I hope this tutorial helps you better understand how optimization tools like NUV Optimization can be applied to real mathematical problems.